Most quantum mechanical systems are in fact infinite. And so whenever we have systems where we only have a few modes, we're always making strong approximations. And often those approximations are incredibly valuable because the real dynamics of the system is restricted to a few modes. So typically we might have a Hamiltonian for a pile of atoms, and it might look something like that in the position basis, which is of course an uncountably infinite basis, and each mode of that uncountably infinite number of modes has a countably infinite number of possible particle occupations. And we can put that into some other basis. And if we choose our basis well, we might get to the point where we can say that only a finite and small number of those modes are relevant. In that case, we can finally make a lovely, useful approximation, for example, something like this. And of course, there are more possible coefficients between those first two modes, but maybe those other coefficients are zero. Alright, so that's the basic idea. Let's have a couple of examples where we actually look at some physics using this idea for the calculation. Suppose we have a screen, and above that screen we have a large number of atoms trapped in some trap. Indeed, we might have them in two traps, well-separated parts of one trap. And we're going to cool those atoms down until they're something like a Bose-Einstein condensate. And then we're going to release them in order to make them come together. And so they're going to come together at a fair amount of speed. And so these two atomic clouds are essentially single mode because they're coming from Bose-Einstein condensates. So they have very narrow momentum width, and they're coming together with a comparatively large relative momentum. The field operator describing the atomic field can be written in any other basis. And in this approximation, we're going to ignore all the modes except for two of them. And those two modes are going to be the two monochromatic plane waves. The other modes are still there, of course, but they're always going to be in the vacuum because there's no atoms in them, and we're not expecting atoms to go in them. Now, even though these are the two relevant modes and all the other ones are irrelevant, we still want to know this operator here because our natural observable for this system is in the position basis. So if we think about these particles falling down and hitting a detector when they make some kind of potential interference pattern, then that detector is going to detect where the particles are. And so the observable it's going to be measuring is really the density observable. So the first thing we'll learn is this expectation value here. And that expectation value we can get just by substituting in our expansion. And now we can think about what we might expect to see on the detector depending on what the actual state of the system is.